Welcome back, students. In today's lecture, we will investigate colligative properties. These are properties of liquids that change as a function of the solute concentration. And these properties only depend on the concentration of solute, not on the identity of solute. The learning goals for today are to explain colligative properties both quantitatively and qualitatively. So we want to understand why having something dissolved in solution would change its properties and how having that thing dissolved in the solution changes its properties. And then at the end, we're going to briefly look at soldering, which is kind of like a melting point depression for solids. So we'll see how that works as well. Before we start, we're going to look at the Gibbs-Duhem equation. This is relevant for some colligative properties, and we'll see it more in the next lecture. This equation relates how the changing chemical potentials of a solution changes. So the way this equation starts is we look at the change in Gibbs free energy. The change in Gibbs free energy is, of course, equal to how it dissolved changing. So the Gibbs free energy change can depend on temperature, pressure, and then if we have a two-component solution, the number of moles of substance 1 and the number of moles of substance 2. For most situations, we have constant temperature and pressure. So these two terms drop out, and our dG simply equals the chemical potential of substance 1 times the changing number of moles of substance 1 plus the chemical potential of substance 2 times the changing number of moles of substance 2. We can then integrate this expression, and then we have to take the derivative of that again. And what happens when we do this is we are realizing that if we're changing the concentration here, for changing the number of moles of substance 1 and 2, the chemical potential is a function of the number of moles of substance 1 and substance 2. So the chemical potential changes as well. So we can also write the change in Gibbs free energy as the chemical potential of substance 1 times the change in the number of moles of substance 2 plus the number of moles of substance 1 times the change in the chemical potential of substance 1. And we do the same thing for substance 2. Setting these two equations for dG equal to each other, we end up canceling out this term and this term, leaving only N1 d mu1 equals N2 d mu2. We can rearrange that to find that the chemical potential of number 2 changes in an opposite way to the chemical potential of substance 1 based on the ratio of moles. And we can also write that as the mole fraction. So if the chemical potential of substance 1 increases by a certain amount, the chemical potential will decrease by a different amount based on the number of moles of substance 1 and 2 in my solution. And we'll see some applications of this in the next lecture. So going to colligative properties, the thing that we are interested in, these colligative properties, like I mentioned at the beginning, are properties that change based only on the concentration of a non-volatile solute. So a non-volatile solute is something that does not easily escape into the gas phase. Some very common examples would be salt, sodium chloride, and also something like sugar would also be a non-volatile solute. And it doesn't matter what concentration of the non-volatile solute that we have these changes in our properties. The properties we're going to look at are the boiling point, freezing point, and the osmotic pressure. We're going to spend most of the time today looking at freezing point because the derivation for the boiling point is very similar. And then we'll talk about osmotic pressure at the end. When you have these non-volatile soluble solutes, they cause a stabilization of the liquid phase relative to the gas phase or the solid phase. And they do this by lowering the chemical potential through these favorable interactions that are formed exclusively with the liquid phase. Why is it exclusively with the liquid phase? Well, think about what happens in gaseous substances. So if you have something like water, you put salt into it. The water can boil, but the salt doesn't boil with the water. The salt is non-volatile. So the interactions that the liquid water is making with the dissolved salt is not present in the gas. So it loses those interactions. The gas is not stabilized by the salt, but the solution is. And the same thing is true with the solid, because when you have crystal ice, there's no room in that crystalline ice for salt. So it stabilizes the liquid relative to the solid as well. Now, what happens with this is that we move down this line. So if this purple solid line is our pure liquid, the chemical potential of the solution is this dashed line here. And that, of course, just like we saw before, changes where these things intersect. So now the intersection between the liquid and the solid is lower, leading to a freezing point depression, and the intersection between the liquid and the gas is higher, leading to a boiling point elevation. So adding some salt to water will lower the melting point, making ice outside melt if we need to salt the roads, and it will also raise the boiling point, which will allow us to boil water at a hotter temperature and do things like cook pasta faster. We're now going to seek to describe these processes mathematically. The reason we're doing this is because we can. And if we have this equation, we can then determine things like how much salt do we need to add to increase the boiling temperature of water to a certain degree, or how much salt we need to add to make the ice in the road thaw, and even how low can we lower the melting temperature. So at what point do we no longer need to salt the roads because it's too cold and the ice snow won't melt either. We are going to consider the freezing point depression. So we are going to consider a solution with this non-volatile solvent in equilibrium with the solid phase. So what we have then is the chemical potential of the solid, and this is the solid solvent. So if we had an ice water solution, this would be pure ice. And we'll put this star here to denote that it's pure. The chemical potential of the solid is equal to the chemical potential of the solution when they're in equilibrium. And the chemical potential of the solution is equal to the chemical potential of the solvent. So we have the pure solvent plus RT natural log of X solvent. We've seen this kind of equation before. So we're having some different chemical potential by the fact that we have a mixture. We can rearrange this equation to obtain that the natural log of the mole fraction of the solvent is equal to the chemical potential of the solid minus the chemical potential of the solvent over RT. Now, what is this? We have the chemical potential of the solid minus the chemical potential of the solvent. Remember that the chemical potential is the molar Gibbs free energy. So this up here is nothing more than the molar Gibbs free energy for solid minus the molar Gibbs free energy for the pure solvent or the liquid. Now this is the opposite of the fusion process, going from solid to liquid. Here we're going from our initial state to our final state. We're going from liquid to solid. So that means that this numerator here is simply the negative change in free energy for fusion divided by RT. So the natural log of the mole fraction of solvent is equal to the negative delta G of fusion over RT. We're interested in how the melting temperature changes as a function of solute concentration. For now, we're going to be using the mole fraction of solvent as a marker of our solute concentration. So for example, if the mole fraction of solvent was 0.95, that means we would have 0.05 moles mole fraction of our solute. We'll change that at the end. What we're going to do now is try to figure out how this changes as a function of temperature. And to do that, we're going to take a derivative of this based on the mole fraction. So we'll go ahead and take a derivative of this equation. So this side and this side of the equation based on the mole fraction. So that will give us d dx solvent of the natural log of X solvent at constant pressure is equal to the partial derivative with respect to the mole fraction of the solvent of now negative delta G fusion over RT at constant pressure. This is a pretty easy derivative here. The derivative with respect to X of the natural log of X is simply 1 over X. But what do we do with this guy over here? Well, we're going to use the chain rule. And so for the chain rule, we're going to take the temperature derivative of this. So we'll say that this is equal to the temperature derivative of negative delta G of fusion over RT at constant pressure. And then to do the chain rule, we'll have to multiply this by the partial derivative of a temperature with respect to the mole fraction at constant pressure. We do this because we've already evaluated this integral. We did that for the equilibrium constant. We know what that is. So this gives us 1 over the mole fraction of solvent is equal to delta H of fusion over RT squared. So if you don't remember, you can go back and watch one of the earlier lectures from chapter 6 where we evaluated this derivative here. And then we simply have partial derivative of temperature with respect to X solvent. And then now we're in a situation where we can figure out how the solvent is changing as a function of temperature. So we can multiply the partial derivative of solvent over. That will give us dx solvent over X solvent is equal to delta H fusion over R, and then I'll write here dt over T squared. So now we can integrate this with respect to mole fraction and temperature to figure out how the temperature is changing as a function of mole fraction. So we'll integrate, and our bounds will be starting at 1, which is pure solvent, to whatever our new mole fraction is. And then for the temperature, we'll integrate from the original temperature of fusion, whatever that was, the initial melting point, to whatever our new temperature is. And we've done this integral a good number of times before. What we end up with is the natural log of X solvent is equal to negative delta H fusion over R times 1 over T minus 1 over T fusion. It is often more intuitive for us to calculate a change in the melting temperature rather than the actual melting temperature. So we can do some rearrangements here to express it in this way. We'll use an approximation that 1 over T minus 1 over T fusion is approximately negative delta T fusion over T fusion squared. Now we do this, and this is actually a reasonable approximation. So if we use water and we say we're doing something to water to change the melting temperature by about 20 degrees Celsius, that would give us here 1 over T would be now 1 over 253 minus 1 over 273. And we're saying that this is approximately equal to negative 20 over 273 squared. And plugging in numbers for this, if we actually go through, use our calculator and figure this out, this first one over here, the actual value is 2.9 times 10 to the minus 4, and the approximate value is 2.7 times 10 to the minus 4. So it's pretty good, especially for small changes. If the change was even smaller than 20, you would be even closer together. So this is an approximation that we can use. We can then say that our natural log of X solvent is equal to delta H fusion over R times delta TF over T fusion squared. And if what we want is delta TF, we can rearrange and solve for that. So we can say that delta TF is equal to the natural log of X solvent times T fusion squared, or RT fusion squared, divided by delta H of fusion. Now, what you probably noticed is that the mole fraction of solvent is kind of a weird way to describe the concentration of the solute. And so it's more intuitive, again, to describe this rather than having a mole fraction of solvent be a concentration of the solute. And we're going to actually use a pretty weird concentration that you probably haven't heard before, called the molality. So the molality is very similar to molarity, but it's not the same. And the molality is defined as the moles of solute per kilogram of solvent. So I'll go ahead and write that for us here. The molality is moles solute per kilogram of solvent. And this is a more useful unit of concentration than the mole fraction. So we can express the mole fraction in terms of the molality of the solute, and we can do that as follows. So the natural log of the mole fraction of the solvent is going to be equal to the natural log of the number of moles of solvent divided by the number of moles of solvent plus the number of moles of solute. And we can define the number of moles of solute as the molality, lowercase m here, of the solute times the number of moles of solvent times the molar mass of the solvent. And when we do this, we can cancel out now all of our moles of solvent there. They appear in every term. And this gives us the natural log of 1 over 1 plus the molality of the solute times the molar mass of the solvent. And we can rewrite that, of course, as the negative natural log of 1 plus the molality of the solute times the molar mass of the solvent. We can now use a Taylor series approximation to say that the natural log of 1 plus a small number is approximately that small number. So the natural log of X solvent is in approximately the negative molality of the solute times the molar mass of the solvent. We can plug this back in for the natural log of the mole fraction of solvent to give us that the change in the temperature of fusion, so the change in the melting point, is equal to negative R times the original melting point squared times the molar mass of the solvent over the enthalpy of fusion squared. And now we take this and multiply this by the molality of the solute. And what you'll note here is that everything in this equation that I've written together is a constant. So all of these things are constant. We can group them together as one. And the only thing that's changing, or that could change, is the molality of the solute. So you see that the more moles per kilogram of solute that we have, the greater the molality, the greater the change in the freezing point depression. And it has a negative sign, so it will go down, it becomes smaller. We can go through the exact same process to get an almost identical equation for the boiling point elevation. We end up having that delta T of boiling is equal to R times the temperature at which the boiling normally happened, times the molar mass of the solvent. And now instead of the enthalpy of fusion, we have the enthalpy of vaporization, times again the molality of the solute. And we can also put that into Kb times the molality of the solute. And so this describes the both the freezing point depression and the boiling point elevation. Here we can look at a table of some substances with their standard freezing points and their constants here that talk about the freezing point depression and boiling point elevation. If we look at water, we can see that water has a Kf of about 1.86. So doing some calculations, we can look up the solubility of something like salt in water and see that salt is soluble to about 6 molar. Since water has a density of 1 gram per liter, 1 kilogram per liter, the molality and the molality and the molarity are approximately the same. So we can say that we can get to 6 molal salt. Multiply this by 6, we get about 12. So with salt, we can expect to lower the freezing point of water by about 12 degrees, which is why once it gets super duper cold, it doesn't quite work anymore. And so this is, of course, just a back of the envelope calculation. Salt is going to be less soluble at lower temperatures. But once it gets into the teens and so forth of temperature, the salt no longer works, it's no longer soluble enough to actually cause the ice to melt anymore. We can also apply freezing point depression to solids. So we can imagine what happens when we have a solid here. And when I'm saying solid, I mean something like a metal. So if we have a metal, these metals also have melting temperatures. And it turns out if we make a mixture of 2 metals, we can change the melting temperature. So in general, we'll have a melting temperature of 1 metal. And as we increase the mole fraction, so as we add in some other substance there, we can cause that melting point to decrease. Now, once you get to these higher concentrations, it makes more sense to describe the other component as the solvent instead of the original component. So we can go through the other direction and have a different curve here. And what happens when we have these two solids together is we end up with this point in the middle. And this joint minimum where these two curves intersect is called the eutectic temperature, which is Greek for easily melted. So a useful example of this is between gold and silicon. So here we can see increasing here is the atomic percent of silicon. And so there's a sweet spot at 18.6%. Now, if we look at this as a melting temperature, this is way low. So pure gold melts here at about 1,050. Pure silicon is melting at about 1,350. But at this particular ratio of gold and silicon with 18% or 18 to 19% silicon, it's melting at like 350 degrees Celsius. So we have a crazy drop here. Now, this is useful because if we take something like gold and put a piece of silicon onto the gold and heat that up to about 350 degrees, that interface is going to melt. While that real gold and the pure gold and the pure silicon don't melt, the interface does melt and sticks together. And then if the temperature is taken away, now those two things are soldered together and they're stuck together. And this process is used to make computer chips with gold and silicon. It's also used in old-fashioned soldering to solder two pipes together, something like that, where you can make metals melt at temperatures where the normal metal doesn't melt, but this mixture does. The last thing we'll talk about today is the osmotic pressure or osmosis. So osmosis is a process by which solvent flows through a semi-permeable membrane. So what do I mean by that? We've already discussed in class that substances like to diffuse and dilute themselves as much as possible. So if we mix 2 equal volumes of 1 molar salt water and pure water, we expect a new solution of 0.5 molar salt water. That salt water will distribute equally throughout both volumes of solution there. Now, the question we ask is what happens if we do this with a semi-permeable membrane that the salt can't actually get through? The two water solutions want to reach equilibrium. They want to dilute themselves as much as possible, but the salt can't flow through the membrane to accomplish this. So instead, what happens is that pure water will flow into the salt water to dilute it. So if we had 2 equal volumes, we put the salt water in with this membrane that only water can go through, that would actually swell up as water would flow into that in an attempt to dilute it. This creates a pressure differential that's shown here, where the pressure inside is greater than the pressure outside by this additional pressure called the osmotic pressure. We can describe this using the Van't Hoff equation, and this actually looks pretty similar to PV equals nRT. We have P, now the osmotic pressure is equal to the moles of solute times RT over V. For seawater with a 1.1 molar NaCl, which is approximately the salt concentration of salt water, the osmotic pressure, we can calculate it using this equation and get it to be 27.2 or so bar. This means that there's an osmotic pressure if we put 1.1 molar salt water into a solution of pure water, that pure water would flow in and increase the pressure up by 27 bar. So if we apply an external pressure greater than 27 bar, what happens is we actually reverse this process. Water is no longer able to flow in since it's under a higher pressure than the osmotic pressure. Instead, the salt water flows out from the salt water and becomes pure, and we actually get pure water from that. This is a process called reverse osmosis, and it's used to do things like provide water for big cruise ships, and it's also used to purify bottled water. So the next time you have a bottled water, you can look, if it's something like Dasani, it'll say purified by reverse osmosis in there. In the next lecture, we will go back to looking at solutions and describe the ideal dilute solution. This model is more applicable to solutions as they need only be dilute but not necessarily have perfect interactions in obeying Raoult's law. And we'll look into this in the next lecture.